So in our universe, whenever we have objects with mass, they feel attractive forces towards each other. For example, let's say we had this 2 kilogram red book, and let's say we had this 1 kilogram yellow lemon. Because both of these objects have mass, they're going to feel attractive forces towards each other. They're both going to feel forces attracting themselves towards each other. For example, let's say we had this 8 kilogram bowling ball and this 1 kilogram lemon. They both have mass, so therefore they're going to feel forces. They're going to feel actual forces attracting them together. And again, the same thing with this bowling ball and this book. The point is, all objects with masses feel attractive forces towards each other. So we have these two objects, they both have mass. We see they both have mass, so therefore they're going to feel forces. They're going to feel these forces attracting them towards each other. However, how do we determine the magnitude of this force? We know they're both going to feel forces, but what is the magnitude of this force? Well, to determine that force, we use a simple equation. The force that these objects feel is equal to this large G, this big G, which just equals 6.67 times 10 to the negative 11 using SI units. So this is just a constant. I recommend you just memorize this. This is just a constant you can find in any textbook. So that's G. M1 represents the mass of object 1. M2 represents the mass of object 2. And R represents the distance between the center of these two objects. So therefore, we can determine the magnitude of this force. We plug in this big G, we plug in this 2 kilograms here, we plug in 1 kilogram here, then we would need to find the distance between them, and we would have to plug that distance here. And based on the way the equation works, this R, which again is the distance, gets squared. But if we knew all those numerical values, we could just plug them in. So again, we plug in this G, this constant, we plug in the masses of both objects, and let's say for simplicity they're 1 meters away from each other. We would plug in that 1 meter, again, based on the equation it gets squared, and now we just calculate. We just plug in all these values in the calculator, and we calculate, and we would get our force. And our force would equal 1.3 times 10 to the negative 10 newtons. So that's a force. Both of these objects feel this force. This 2 kilogram book feels a 1.3 times 10 to the negative 10 Newton force in this direction, and this yellow lemon also feels that same magnitude of that force in this direction. And something important to realize are these are a pair of Newton's third law, these equal and opposite forces. They're equal in magnitude, they both have the exact same magnitude, and they're opposite in direction. This force points in this direction, this force points in this direction. So this is a pair of equal and opposite forces. And you might wonder, this book is twice the mass. It has a 2 kilogram mass while this lemon is 1 kilogram mass. So therefore, because this has a higher mass, shouldn't it feel a stronger force? Well, no. Again, these are equal and opposite forces. So something else we might wonder is what determines the magnitude of this force? We know they both have masses, so therefore they're going to feel these attractive forces. But how do we determine what affects the magnitude of this force? Well, again, we know what determines the magnitude of the force. It's these variables. And we know this is a constant, so that's constant. However, we see as these masses increase, the force increases. So as if maybe we had a larger lemon with a larger mass, this mass would increase, so therefore the force would increase. So that's one thing that affects the magnitude of this force, the masses. And also we see the distance. The distance is also in the formula, so therefore it also impacts the magnitude of this force. And based on the way the equation works, the larger the distance between them, the larger the denominator, the smaller the force. But again, that's just simple algebra, just the way this equation works. But now you might wonder, for example, let's say we had a book, let's say we had this table. Let's say we had this table. We know they're not going to move. If we have this book and this lemon, we know they're not going to move. We know they're not going to spontaneously just force and collide and hit each other. So what's going on? Because we know whenever objects have masses, if we have a table with a book and a lemon, we know the book has mass, we know the lemon has mass, so therefore according to this equation, we know they're going to feel forces. But we know in our everyday experience, they're not going to move. Why? What's going on? Well, yeah, this book is feeling a force, but it's not enough to overcome the static friction. There's also static friction force, resistive force. So therefore, even though they do both feel forces, but they just don't overcome this friction. But again, the point is, all objects with mass feel attractive forces. This book has mass, and this table has mass. So therefore, we know they're going to feel attractive forces. This earth has a mass. This lemon has a mass, so they're going to feel attractive forces. All objects with masses feel attractive forces. So now that we know this, let's do another example. So we know if we have this earth, and let's say the mass of earth happens to be around this 6 times 10 to the 24 kilograms, a huge mass because the earth is huge. So we have our earth and we have this book. We know they both have masses. The earth has mass, the book has mass, so therefore we know they're going to feel these attractive forces. They're going to feel forces towards each other, these equal and opposite forces towards each other. How do we determine the magnitude of that force that both of these objects feel? Well, again, we know we can just simply use this equation and just plug in our values. So therefore we have we know this is just G, this is just a constant. We know we have a 2 kilogram book. We know we have this 6 times 10 to the 24 kilogram earth. And then we would also need to know the distance between them. But the distance between the center of this book and the distance between the center of this earth. We would need to find that distance. And really, the radius of the earth is around this value. So that's close enough. That's close enough because really this little distance doesn't really make any difference. So therefore, we can use the radius of the earth as a proxy to determine the distance between the center of this book and the center of this earth. But now that we know all those numerical values, we can just plug it in our formula and we would get the force. So now we know. Now we know these forces that this book feels towards the earth and that the earth feels towards the book would be 20 newtons. And again, this is really estimate because really we're estimating the mass and we're estimating this distance, but a rough estimate is around 20 newtons. So now we know the book is going to feel a 20 newton attractive force towards the earth, and the earth is going to feel a 20 newton attractive force towards the book. So now let's quickly get rid of the table and replace it with our hand. So now we have our hand and we're holding on to this book. We know we're holding on to this book and we would feel this force. We would feel this 20 newton force in our hand. And we know this because we could put this book, imagine putting a book on your hand and closing your eyes. You can feel the book. Even though your eyes are closed and you don't see the book, you can feel it. Why can you feel that book? Because again, it's this 20 newton force, this force towards the earth. But now what would happen if we dropped the book? What would happen if we let go and we dropped the book? Well, again, we know the book has mass and the earth has mass. So therefore, as long as we know those masses and we know the distance between the center of both of them, we can determine this force that they will both feel. So now we know this book will feel a 20 newton force. So now we know it's feeling a force, so therefore it's going to accelerate. It's going to accelerate downward. And that's why if you have a book, you know it's just going to fall. If you just drop a book, well, you know it's going to fall because it feels this force. So now we can do some calculations. What's going to be the acceleration? Well, now this is just simple Newton's second law. We know force equals mass times acceleration. So if we know the force that an object is feeling, and we know the mass of the object, we can determine what the acceleration must be of the object. And that's a simple application of this Newton's second law. And this is true for any 2 kilogram mass that's feeling a 20 newton force. We can determine what acceleration it must be feeling. So again, just some simple algebra. So with some simple algebra, we would again divide both sides by the 2 kilograms. Now we get this. And now we would solve for the acceleration, which would be roughly around 10 meters per second squared. So now that's the acceleration. Now we know if we have a 20 kilogram book that feels this 20 newton force, we know it's going to accelerate. What's going to be that acceleration? 10 meters per second squared. But remember, this 20 newton force was an estimate, because it was an estimate. This was an estimate because we estimated this mass and we estimated this distance. So really this was an estimate. It wasn't exactly precise. But if we were more precise, if we did a very precise mass and we did a very precise distance and found that force, and then if we use that force, we would get an acceleration of roughly around 9.8 meters per second squared. So this is the more precise acceleration. So now we know this book is going to feel an acceleration of 9.8 meters per second squared. And we know this is the acceleration due to gravity. You've probably seen this little g equals 9.8 meters per second squared. You've probably seen this. And this is the acceleration that all objects feel due to this force of gravity. So the point is, objects with masses, they feel these attractive forces. And these attractive forces are the force of gravity. This 20 Newton force is the force of gravity. So again, we know this book, due to gravity, it feels this force of gravity and it's going to accelerate. What's going to be that acceleration? 9.8 meters per second squared. And you've probably seen you can determine that force of gravity that an object feels. If you know the mass of that object and you multiply it by this g, this acceleration due to gravity, you can determine what the force of gravity must be. So we could do this. We know this book has a mass of 2 kilograms. We know the acceleration due to gravity, so we can determine what that force of gravity must be. And again, we would get roughly around 20 newtons. So now we know. But this 9.8 meters per second squared is the acceleration due to gravity of any object, whether it's a 10 kilogram book, or even if maybe we had a 10, or if it's a 2 kilogram book. If it's a 2 kilogram book, it'll feel an acceleration of 9.8 meters per second squared. But also if we had a 10 kilogram book. If we had a 10 kilogram book, it would also have this exact same acceleration due to gravity. And even if we had a 70 kilogram book, or etc., it doesn't matter. It will always feel the same acceleration due to gravity of 9.8 meters per second squared. So let's prove that. Well, again, we know what's going on. We know we have a 10 kilogram book. We have the 6.6 times 10 to 24 kilogram Earth. They both have masses, so we know they feel those attractive forces. How do we determine the magnitude of that attractive force? We know we determine that using this equation. We plug in both masses, and then we do an estimate of the distance between them, which we can estimate based on the radius of the Earth, because that distance is essentially this little extra distance does make a difference. So now we can plug in all those values and determine what this force of gravity must be. And we would get a force of gravity of roughly around 100 newtons. So now we know this book feels around 100 newtons worth of force, and that's the force of gravity. And again, we know the Earth also feels 100 Newton force of attractive force moving towards the book, because again, these are a pair of equal and opposite forces. So now we know this 10 kilogram book feels around this force of gravity. So now using Newton's second law, we can determine what the acceleration must be. If we have a 10 kilogram mass feeling 100 Newton force, we can determine what that acceleration must be, and again, we would get that same acceleration. Again, we would get that acceleration of roughly around 9.8 meters per second squared. So this is the acceleration due to gravity of all objects, whether it's a 10 kilogram book, or a 70 kilogram book, or a 2 kilogram book. And the truth is, this acceleration due to gravity does vary the farther you get away, because if you get really far from the surface of Earth, then this distance does change, and that complicates the situation. But the point is, the big picture idea is all objects with masses feel attractive forces. For example, let's say we're in outer space and we have this planet and this planet. We know they both have masses. So because they have masses, we know they're going to feel those attractive forces. They're both going to feel attractive forces towards each other. These equal and opposite forces. These pairs of Newton's third law, equal and opposite forces. And these forces that these objects feel due to their masses, these forces are the forces of gravity. This is the force of gravity. And again, this is true with all objects with masses. For example, if we have this Earth with mass and this human with mass, we know they both have masses. We know the human has mass and the Earth has mass, so therefore we know they feel those attractive forces towards each other. And that force that this human feels towards the Earth, that's the force of gravity. And that's why if we jump, we fall straight down towards the Earth because that force of gravity.